Thank you. First, I wanted to say that was a great talk, Dan. Uh, I'm more on the AI side, and so it was really fascinating to see these types of true data coming through. Like Dan did, I'm also organizing my talk in three different buckets, and actually, it's more like a ladder, and I'll talk about them as we go. So, I'm Sriram. I'm the director for Center of Machine Learning at University of Texas, Dallas. Um, I've been a long-time collaborator with Christian. So we had about I think 11 PhD students till the end of last year, and suddenly we are down to 6. We had 5 students defend during this pandemic. Um, so thanks to all my PhD students, my key collaborators, and of course several funding agencies for funding our research. So what is human-allied AI? So the way we think about human-allied AI is, can we build systems that can seamlessly interact with, learn from, collaborate, and potentially teach the human expert? So in our vision, human-in-the-loop systems don't stop at just using humans for getting labels, but things beyond labels as domain knowledge, as constraints, and so on. So I'll explain what we get as we go. So to do that, it's important that this system be explainable and interpretable to the human, so that and it should speak the language of the human, not the language of the machine. So it's really important that we build systems that can actually convey to the human what it's learning, and more importantly, know what it knows, and ask questions about what it does not know. In a short answer, the goal for us is to create systems that behave like children, that students that are trying to learn. Okay, so for the classic scenario that we are envisioning is the agent, which we call a statistical relational learning agent or Starling agent, is sitting inside the computer. Now, somebody goes to the physician asks a bunch of questions, and then recommends a treatment plan. And then what happens is that the agent now looks at this and says, no, wait, you're missing the most important thing. This person has diabetes. Oh, well, the physician says, well, I know, but the person is in acute pain, so I'll bump up the medicine, and we have to take care of this first. Or the physician could say, oh, thank you for letting me know. The patient did not tell me, so I'm going to take care of it. So the point is that this is allowing for a richer interaction between the learning agent and the expert by observing the physician. The picture I have here is this domain that I'm working with currently, where we are interested in predicting adverse pregnancy outcomes. This is in collaboration with the Regan Street Institute at Indianapolis and Northeastern Boston, where we have a bunch of cohort of pregnant women. And the question that we are having is, several questions we are looking at, but the one main question that we're looking at is, which of these women are going to develop gestational diabetes, and which of the women who develop gestational diabetes will go on to have type 2 diabetes, and trying to see if we can somehow figure out early interventions that can prevent this from happening. So this is our most recent grant that we are working on. And as you can imagine, the most important challenge in all this, while there are many other challenges like scale of the data, the temporal arrival of the data, the multitude of the features that can explode. Most importantly, not all of us give the same amount of data. And so there are many simpler challenges to more complex challenges like partial observability, long-term decision-making, and so on. The most crucial challenge of all is the humans. Because humans, we are reasoning really approximately, but we expect the system to be exact, right? We act extremely unpredictably. If my student asked me a question last week, the answer might be different to what I'm saying this week, right? And that could be because I've learned something, or just that I didn't have my morning coffee. So we are very unpredictable in how we are doing how we are making our decisions, but we expect the system to be extremely predictable, right? So to do this, I think it's really important to understand an approximate human model, right? So it's kind of like, okay, if we can't expect the same reaction from the human for the same type of interactions all the time. So we need to make sure that we understand what the human is trying to do. So this is something that we are trying to do currently, is trying to model the human and try to understand what he or she is looking for and how we can make that to work. Okay, so to do that, in our head, there are three crucial steps for human-allied AI. The first step is where we need effective and efficient reasoning systems. Systems that can operate on data, but are very effective, very efficient, and more importantly, generalizable, okay, and explainable, because they need to be presented back to the human. Of course, the problem here is that we treat human as mere labeler and we ignore the human knowledge. So the second step that we consider is the one where we allow the human to provide richer domain inputs, right? Where we treat the human as more than a mere labeler. So we take some advice, some guidance as constraints that allows for robust learning using these constraints. The third step is where we are closing the loop, okay? So in the second step, we take these constraints for learning, but they are taken before learning actually commences. So in some sense, these constraints serve as some sort of an inductive bias for the learning system. In the third step, the goal is to build an intelligent student. So where the idea is that the agent will know what it knows and ask what it does not know. I have a 4-year-old or 5-year-old, it's going to be 5 soon. And nowadays when I tell him something, he goes, shh, I will ask you when I want. Okay. But 3 years back, I was able to tell him what he needs to do before the task commences. But now he's growing up and he's like, no, you wait, I will try. And if it doesn't work, you tell me what to do. And so that's really the idea that we want to build is, can we build these systems? Because the systems could have a different model than the human, right? And I'll explain that a little bit later. And so the idea is that if we properly close the loop, then maybe the system will be able to find new things that the human doesn't and potentially teach the human back because they have established the communication paradigm, right? So those are the 3 steps. So I've organized my talk in these 3 steps. So initially I'll talk about learning only from data, and then allowing for some constraints before learning, and then soliciting these constraints during learning. And for each of them, I'll talk about some of these clinical tasks that we looked at. So our effective learning is really built upon this idea of functional gradient boosting. And the idea in functional gradient boosting is very simple. You start with an initial model, okay? And then you look at the data, make predictions on this data, compute the gradients. The gradients become the weights of these data points. What you do is you learn a new model to fit to these gradients. Now, not to the original data, but only to the gradients. Now add this to the model and keep going until convergence, right? So let's just take 2 examples, right? Let's say we are interested in predicting who has diabetes, okay? So let's say I'm a positive example and I have diabetes. Dan looked very healthy, and so maybe he doesn't have diabetes. So according to the data, my probability of having diabetes should be 1 and Dan should be 0, right? So now let's say my initial model predicted that Sriram has a diabetes probability of 0.8. Okay, so my gradient would be 1 minus 0.8. 1 is because I have the diabetes, so the probability should have been 1, but my model predicted it as 0.8. 1 minus 0.8. 0.2 is my weight. For Dan, let's say the model predicts with 0.15 probability. His value should have been 0, but it's predicting as 0.15. 0 minus 0.15. Negative 0.15 is Dan's probability. So in some sense, Dan's gradient. So what happens is that every positive example, as you can quickly see, because of a 1, will have a gradient greater than or equal to 0. Every negative example will have a gradient less than or equal to 0. So you're trying to push all the positive examples towards 1 and all the negative examples towards 0. And these intermediate smaller models are learning only on these gradients, not on the full data. Okay, so and the learning continues this way until convergence. And what we have done is we have applied this on a whole bunch of problems, all the way from learning graphical models, both directed, bidirected, undirected models, to continuous time models. So we had an effective learning for continuous time Bayesian networks and applied it on a cardiovascular disease data set and got some great results. We have learning from hidden latent models, learning from demonstrations, recently working on neural models as well. But there is one that I want to talk about, one case study. And this is something that we've done some time back, but I still want to, it's actually one of the more interesting problems that I worked on, where we are interested in predicting coronary artery calcification, which is basically these calcium deposits on these arteries. And the goal was, so the goal was to work with a group where the data was collected from 1985 until we were looking at the data till 2010, and now we have data till 2020. So 1985 to 2010, and participants were between 18 and 30 in 1985, and they kept following them every 2 to 5 years and collecting all the data, and they had a whole bunch of data. And we looked at a few specific features, including their blood pressure, cholesterol, and blood sugar level, and so on. Just about 20 features or so from 1985 till 2010, and predicted if they are going to have the CAC formation in 2010. Voila, we got the best results using this gradient boosting, functional gradient boosting. We call it as R because we were looking at time as a relation and basically applied a relational gradient boosting. And compared to the other methods, the results were super impressive. But this is not really the more interesting part for me. Then we also provided a way where you can combine these trees to form a single tree. So if you look at a single tree, you can look at some interesting data points. This tree is going to be hard to read. So what I will do is I'll just read it for you so you can understand. And I'm just going to focus on some important aspects, right? So the first is that the tree always split on the gender. And again, this is an important indicator for heart attacks because men are more prone to have heart attacks. And of course, the heart attacks could be more lethal in women. So this says that the gender of the person is male, and the person was between age, let's go this part where it says that age was over 35, over 45. This person was actually quite older in 1992, but the cholesterol level was pretty high, between 200 and 400, and they smoked. Okay, so this is the path. So left is true, right is false. So I'm following this path, which says it's a male who's over 45 and who smoked in 1992. Sorry, who had a high cholesterol and was a smoker in 1985. Then the probability of a calcification was like 0.97, as against a female who did not smoke in 1990, who had a 5% chance of calcification, or who smoked, but the LDL was between 0 and 100, and there was no blood pressure. Okay, then it was 0.2. So you can see that the person, the male who had a high cholesterol and smoked, had about 5% more chances, 5 times more chances of calcification than a female smoker, but who had a low cholesterol and low blood pressure. Okay, and the more insightful things that we got was that actually after a year about 7 or 10, which is 1995, there was not much we would learn. Even adding more data did not seem to change much, which told me more about the people than about the disease itself. That people don't change, that many people don't change with time. So I made this joke saying that once a slob, always a slob kind of a thing. So people who were in 20s and 30s not very active, at least in this cohort, seem to not be active in their later years as well. And of course, we also looked at more interesting things like learning only from socioeconomic data. We threw all the clinical data, and I'll just again read this part alone, which is saying that in the year 2000, when they were in their 40s, they were still in school. They kept smoking regularly. They did not pay for their residence, which means most likely they stayed with their parents, and they still had children. Okay. And then the probability was 0.89 or close to 0.9. Okay, so this person is extremely stressed. No work, was a regular smoker, did not pay for the residence, and still had kids. As against somebody who, for instance, who had a stable job on the right side, who did not smoke a cigar, and it just says married. I want to say happily married, but let's say that they've been married for at least 10 years. Okay, so they are in a stable marriage, has not smoked cigars, and have a stable job. They have a 0.1 chance of getting, so 10% chance of having a calcification. But the key thing is that they have 9 times less. They are 9 times less likely to have calcification. So we were able to generate these models that were presented to the domain experts. Of course, they were all very excited about this. And we got similar results on other domains as well. And I'll talk about them if needed later. We constructed temporal models to see how they evolve, all based on gradient boosting. And the more interesting things, you can see that smoking was something that people did not give up that much, or the opposite. When people exercised a lot, they kept exercising. So you got these interesting relationships that people about work, about occupation, and so on. So it's pretty interesting to see and tease out these models over time. Of course, all our code is available online, and the we have an excellent tutorial to go with this. So and we provide support if people need, and so kindly check it out when you get a chance. So this leads me to the next part, where again, so far what we have done is we have used domain expertise only to select our features, okay, and so in some cases discretizing them into bins as needed. In this second part of the talk, I'm going to talk about the case where we take domain expert knowledge as constraints before learning. Okay, so what do these constraints look like? They are essentially polygons in your learning space. Okay, so the constraints are saying that any region inside this black, any example inside this black should be a black example. Any example inside this should be a blue example. Okay, so what it does is that it's a negative example or a positive example, and it just defines the regions of these examples. So that is the literal meaning of these constraints when you project them into your example space. So what are these constraints, right? So the constraints for us would be things like qualitative constraints. So things like, as the BMI increases, the risk of diabetes increases, or a synergistic constraint that talks about higher BMI has a higher risk of diabetes or a higher risk of heart attack with higher A1C than with lower A1C. Okay, so what it does is it talks about two features, BMI and A1C levels, influencing a third variable, which could be the heart attack. Okay, or these could be just simple things like precision versus recall trade-off. In some cases, you need to optimize false positives. In some cases, you need to optimize false negatives. If you're in a recommendation system, you want to maximize precision, not recall necessarily, because I get these emails from LinkedIn saying a postdoc position is open for you at Indiana University. Voila, I was the PI of the grant that they want me to apply the postdoc position to. Okay, and that's because they're maximizing recall as against precision. When we work with, let's say, Ebola or now COVID data, you want to maximize recall, where the worst case you're going to do is quarantine a few people, the false negatives, the false positives, you're going to quarantine them as against when you minimize the false negatives. Okay. The third type of advice could be preferences, where we can say, I prefer that the label be this over this, or I prefer that we do this action over that action. So for instance, I prefer that you bring down the pain before addressing the blood sugar level, because the blood sugar level is under a reasonable range. So you can give these statements as soft constraints to the learning system. Okay, and what we've done is we've used this in the context of probabilistic graphical models, reinforcement learning, imitation learning, planning, and now in neural models. So we've been working on several different learning methodologies for these aspects. And one of the examples that I have is in the notion of KBSVMs, or knowledge-based support vector machines, where you can take an advice as a constraint, as just as an advice that says, if this, I prefer this. And then what you can do is you can take a data and use both of them to move your margin. Okay, and so this is the example actually from the support vector machine paper, where we can move the decision boundary based on the new data point and the constraint that you get. Okay, so the constraints becomes, as I said, polygons in this space. And so again, we have applied this in the context of advice taking and on predicting Alzheimer's. And you can see that the use of advice, which is the because it's an online SVM, it was called as Adviceptron, classic take on advice plus perceptron. So you can see that Adviceptron has much better AUCPR compared to the linear model on many of these tasks. And we have also added this to the gradient boosting, where what we've done is we have taken the advice and added, and so the advice becomes this alpha times the advice plus 1 minus alpha times the data. So at every point when I'm weighing the example, I'm checking if it violates or satisfies the constraints. If it satisfies the constraints, I count the number of satisfied constraints and that weigh it up by alpha, and then the data comes by 1 minus alpha. So it's a linear combination of both the data and the advice, and then you continue doing the same process. Again, we got some excellent results on predicting in Alzheimer's from the image data. We are considering a 3-class problem where we are predicting whether somebody has Alzheimer's, or is it cognitively normal, or in this region in between called as mildly cognitively impaired. And of course, teasing between Alzheimer's and mildly cognitive impaired is a harder problem. And there, we got significantly better results than just using the data. Of course, doing the mildly cognitive impairment versus cognitively normal, the impact was more. We reduced the error by half or more when doing it using the domain knowledge as advice. Again, I talked about many of these advice, monotonicities, recall, and preferences. The final type of advice that we looked at is what is called as privileged information. So these are some features that could be available during training, but not during deployment. For instance, when we were working with this group at Wake Forest, because we were following a bunch of people in their clinical study, we had access to their sensor data, we had access to their cognitive test data, and the electronic health record data and the imaging data. But let's say in a clinic, this person, the physician, has access only to the images and let's say the electronic health record. So what the cognitive tests and the wearable sensor data would serve to do is not actually be in the model, but serve as constraints to drive the model to a better local optimum when you have to choose between multiple local optimums. So this is the type of constraints that we were using while learning, and we applied this in the context of Alzheimer's. So I'm coming to the last part of my talk, where I'm going to talk about closing the loop, right? So as I said, if I have to go back a few slides, right? When I ask the human to provide advice, the human provides, most of the times, humans are very good at stating the obvious things, right? So for instance, the black here is absolutely useless because there are a bunch of data points. If I'm learning a linear model, the black on the top left corner is absolutely useless because giving me that is as good as not giving me that, because I have a whole bunch of examples here which would have prevented my linear classifier from moving there anyway. Okay. On the other hand, the black on the top right is extremely important. So are the triangles on the top right and the bottom left corners. They are extremely important. If I had included another triangle on the bottom right corner, it's absolutely useless. So the point we were trying to make was, somehow can we make the system ask the constraints? The system can say, here are 2 points. Can you tell me what you know about them? And then the human could provide advice as needed. Okay. So sorry, I had to go back and forth here. So the hypothesis that we had was, if you're only learning from the data, let's say you need n times p examples. Okay, so that's the passive learning. So you have n examples that you need. It has been theoretically shown that if you use this active learning strategy to get the labels, you can actually learn a good model, a robust model, in logarithmic number of examples. It has also been shown that if you use these constraint-based learning, then you can actually get to log of the number of examples as well. So it's order of the log of the number of examples. The hope that we have, and we have verified this empirically, we are working on the theoretical side of this, is if we combine the notion of active and advice together, so you have an active advice taking or active guidance elicitation, then hopefully we are in the log space, which is we further reduce the number of log space in our learning strategy, right? So, so this is our goal, and this is where we are going towards. And the problem that we are looking at is in this notion of active feature elicitation, the first problem that we looked at. Again, this is in the gestational diabetes case. So here we had a cohort of pregnant women on whom we had a whole bunch of information. So this is a clinical study called Moms to Be, New Moms to Be, where we have a demographic information, we have the sensor data, we have their sequence data, and we had the notion of whether they have gestational diabetes or not. And the goal for us was to create more recruits to actually learn a better model. So to recruit more people, when we sent out this a questionnaire in Indiana University, we had a lot of people apply at the same time. Whole bunch of people applied, and for whom we have both the demographics information, and we know that whether they have gestational diabetes or not, according to their clinician. The key question that we asked was, should we collect the sensor sequence data for all of them? Okay, and so and the problem was that because we had a whole bunch of people and a limited budget, we had to identify the most informative women who on collecting the sensor or sequence data would help us build a robust model. Okay, so the key question was, whom should we recruit? And so the way we did it was, we looked at the data, and the top part is the part where we have all the features, right? So we have the available features and the newly elicitable features. And so what we did was we ran some form of a scoring function. We learned a model on only the fully observed examples, and learned a model on only the queryable examples, and made predictions on both of them on the training data. And we found the distance between them. So we somehow used a scoring function and found a distance, and we could use anything, Hellinger distance, KL divergence, and we showed that we are robust to the distance metric. But we calculated the distance between the fully observed examples and the queryable examples. And what we did was we ranked them according to the distance, and picked the most diverse set of examples and added them to the model. Sorry, added them to the fully observed cohort, updated the model, kept repeating until our budget was satisfied. So what this allows us to do is kind of fill the cohort slots with the most informative people. Okay. And this was published in HAAI, I think, a couple of years back. And what we showed was, particularly in the case of recall, and in the case of, let's say, geometric mean or F1 score, we had really good performance using this active feature elicitation strategy. That's the blue line. RAND is where we choose people at random. US is the uncertainty, using uncertainty sampling, using only the observed features, and uncertainty sampling using all the features. And what we show here is that we used active feature elicitation with gradient boosting and KL divergence as a scoring metric. We used SVM also, and saw actually better results in recall, a huge jump. But with geometric mean and F1, it was initially dipping, but then it converged to a better solution towards the end. So as later iterations of support vector machine with KL divergence had good results. And we have similar results in other other learning methods as well. And then what we did was, here in this case, when we did this, we assumed that all the elicitable features have equal cost. And that's not true. Putting the sensor data is actually sometimes cheaper than sequencing, right? And some blood tests are much more expensive than let's say, just giving a $50 sensor. So what we did was we introduced a cost-based framework where the features themselves have a cost. And what we need to do is figure out not just the budget in terms of the total number of people you have to recruit, but also the total cost that you have to optimize. So what we did was we added this extra step of including costs, and the elicitable features have their own cost, and we have observable features have their own cost. So each feature set has their cost. And what we wanted to do was use these costs in our learning methods. Again, we looked at several different data sets, and what we did was we created an objective function that had 4 different components. If you want more details, I can talk about this. But looking at this from a submodular optimization lens, we had things like relevance, how much redundant are some examples, and redundant on the label, redundant by themselves. Okay, so how are they looking in terms of their values, and how are they looking in terms of their values conditioned on the label, and of course, what is the penalty of the cost. And then what we did was we came up with a greedy strategy. Again, we got very good results on pretty much many diseases that we looked at. The rare diseases is a data set where we were looking at if somebody has rare disease based on responses to their questionnaire. So the sensitive questions had a cost. Should we ask these sensitive questions or not? PPMI was this Parkinson's disease, the study that we looked at, and the demographic features had lower cost, whereas these imaging features had higher cost. ADNI, I talked about it already, and the last one was actually not a clinical study, but a financial study. But the idea is that it's working on many different types of problems. So I think in my, I kind of motivated, and I'm out of time now, that I wanted to explain that that AI is really more than a single table. You're looking at multiple types of data and relational databases. You need to understand symmetry and learn from these symmetries. So most of our learning methods, I kind of push that under the rug, are using relations, sequential models, and models that understand time. is extremely important. But the most important story that I wanted to convey is that human is an ally in learning, particularly when you're working with domain experts. We should be looking at using their expertise and their decades of accumulated knowledge in building a better system. So, of course, there are many steps before we conclude, right? So we have to deploy this in many problems. And one of our common goals of Christian and myself is, can we build this notion of data science genome, where we can build these machines that read and understand data science publications, and now help new students who are coming in with their learning problem. Of course, the other question is also knowing what is the expert's expertise. So when I have a question about, I don't know, cardiology, I go to my cardiologist. I have a question about my digestive thing, I got my gastroenterologist. So how do I know who knows the most important answers to those questions? And how do we ask them the right questions? The last one that we're really looking at is this notion of thinking fast and slow. Daniel Kahneman books, where we are asking, can we have these signal-based neural models, which just looks at signal data and then combine it somehow with these slow learning semantic models that understand the symbols rather than just talking in terms of the signals. So how do we build these two hybrid models for effective decision making? So with that, I am done. I am ready to answer questions. All the code is out there, so if you want to, you can scan, and of course, and post questions to my Twitter account, or just email me if you don't get a chance now. So thank you.